Welcome to the next lecture of separation axioms in topology. Till now we have done a lot about separation axioms like T0 spaces, T1 spaces, T2 spaces, regular spaces, T3 spaces, and we have also introduced T4 spaces. Some properties of T4 spaces were also being discussed, and now we are moving on to the more theorems and more properties of T4 spaces. The first one, what I am going to take today is this theorem. Write down the statement first. Statement is every closed subspace of a T4 space is a T4 space. So closed subspace of a T4 space is a T4 space. That means closed subspace of a normal space is normal. But we are not saying that normality is a hereditary property. So in fact, to be more clear, let us take here normal space. I am taking here that every closed subspace of a normal space is normal space. To be more clear, we are going to prove that closed subspace of a normal space is normal, and normality is not a hereditary property. For that, I am going to start the proof now. Let X top be a normal space. I have taken a normal space and now I'll take a closed subspace of it, and then I'll prove that the closed subspace is also normal. So let Y tau y be a closed subspace of it. Now Y tau y is a closed subspace. That means Y is a closed subset of X. That means we have taken Y to be a closed subset of X, and now we will show that Y to tau y is also normal. So now we will show that Y tau y is normal. And you know how to prove a topological space to be normal. From where we are to start? We are to start by taking a pair of disjoint closed subsets and then to find a pair of disjoint open subsets containing them. So that is the process which we will follow. Let A, B be closed disjoint, also closed disjoint subsets of Y tau y, you can say, because the topology we are taking here is tau y. Now A and B are closed, tau y closed, and if a subset is tau y closed, then definitely there will be a tau closed subset which will give this closed subset by intersection with Y. So that means there exists, since A is tau y closed, there exists F1 tau closed and F2 tau closed sets such that how this A will be constructed. This A will be some tau closed subset F1 intersected with Y. Similarly, this B tau y closed set, this will be some tau closed set F2 intersected with Y. This will be the way. Now what are F1 and F2? F1 and F2 are disjoint closed subsets of X. Now F1, F2 are disjoint closed subsets of X, and X is given to be normal, and your X is given to be normal. Therefore, there must exist tau open sets G1 and G2 such that your F1 is contained in G1 and your F2 is contained in G2. And now intersect them with Y. So F1 intersection with Y is contained in G1 intersection with Y, and F2 intersection with Y is contained in G2 intersection with Y. G1 and G2 are disjoint. So G1 intersection Y, which is a subset of G1, and G2 intersection Y, which is a subset of G2, will also be disjoint, because if two sets are disjoint, their subsets must also be disjoint. This is clear diagrammatically, you can see. If these two are disjoint, then their subsets must also be disjoint. So that means this G1 intersection Y and G2 intersection Y, they are clearly disjoint. So F1 intersection Y, what is F1 intersection Y is A. So this is your A, and this Y intersection F2, this is your B. So here is your B, and this G1 is tau open. So G1 intersection Y will be tau Y open. So this is your tau Y open set, and similarly this is also your tau Y open set. So let us see from where we have started and at which point we are arrived at. We have started with taking two disjoint closed sets A and B in the subspace tau Y, Y tau Y, and we have obtained two tau Y disjoint open sets such that A is contained in this and B is contained in this, and that is what is the Urysohn's axiom. So that means your Y tau Y, the subspace, the closed subspace of X tau, is also normal. So this was the first theorem we wanted to prove today, and now I'll move on to more theorems. So basically what we are doing, we are making the base for Urysohn's lemma. So next theorem in this series is the theorem is normality is a topological property. It is not hereditary, but it is topological. That means homeomorphic image of a normal space is normal. That what we will prove in this theorem. So the proof now, let X tau and Y rho be topological spaces. Let X tau be normal. Let F from X tau to Y rho be homeomorphism. That means it is 1, 1, it is on 2, it is continuous, it is open. So there is a homeomorphism from X tau to Y rho. X tau is given to be normal, and we have to show that the homeomorphic image of X tau, that means Y rho, is also normal. So to show this Y rho to be normal, once again we will have to take a pair of disjoint closed subsets from here, and we will have to find a pair of disjoint open sets containing the two disjoint closed sets. So I'll start with right from there. Let A, B be row closed subsets of Y such that A intersection B is phi. So these two are closed and are disjoint. Since it is onto, we can take the inverse image. That means, this means your F inverse A and F inverse B. Your F is given to be continuous. That means inverse image of a closed set is closed. If A and B are closed, then their inverse images F inverse A and F inverse B must also be closed. So F inverse A and F inverse B are closed, and F inverse A intersection F inverse B. F inverse A intersection F inverse B, you can write it as F inverse A intersection B. But your A intersection B is phi, so F inverse A intersection B is also phi. That means F inverse A and F inverse B are closed. Where closed? A, B are row closed here, and F inverse A and F inverse B will be tau closed. So these are actually tau closed sets. So you have now two tau closed sets which are disjoint, and x tau is given to be normal. So therefore there must exist two disjoint tau open sets containing them. So therefore there exist tau open disjoint sets, you must say, tau open disjoint sets G and H, such that your F inverse A is contained in G and your F inverse B is contained in H. Also, G and H are disjoint, so D intersection H is phi. Now F inverse A is a subset of G. That means your A is a subset of F of G. Similarly, F inverse B is a subset of H. That means your B is a subset of F of H. Also, F of G intersection H is phi. That means F of G intersection H is also phi, and you can write it as F of G intersection F of H is phi. You can write it like this. Once again, look at your G and H are tau open, and your map F is an open map. So if the map is open, that means image of an open set is open. G and H are tau open, so their images FG and FH are row open. So what you have obtained now? You have started with two disjoint closed sets A and B in Y, and you have obtained two disjoint open sets FG and FH in Y, such that FG contains A, FH contains B, and the FG and FH intersection is phi. And that means your space Y row is a normal space. So that means homeomorphic image of a normal space is normal, or you can say normality is a topological property. And since T1 being a T1 space is also a topological property, that means normality plus T1, that means T4. Property of being a T4 space is also a topological property. And now there is another theorem. We have proved that every T1 space is T0. We have shown that every T2 space is T1. We have shown that every T3 space is T2. And now we are going to show that every T4 space is a T3 space. So for the proof, let X tau be a T4 space. So I have taken a T4 space, and now I will prove that it is also a T3 space. To show that it is a T3 space, it is T4. T4 means it is normal and it is T1. This is given. And what we are to show? We are to show that it is T3. That means we are to show that it is regular and T1. T1 already is given. So that means it is sufficient to show that it is a regular space. That is more than sufficient to show that the space is regular, because T1 it is already. So regular plus T1 will make it T3. So to prove it regular, I'll take a closed subset and take a point which will not belong to that particular closed set. So let F be a closed subset of X, and let X belonging to X be a point such that X does not belong to F. Now X does not belong to F clearly implies that the singleton set X intersected with F is phi. Your space is given to be T4. T4 means normal plus T1. So it is T1. And you know that in a T1 space, every singleton set is closed. That means this set is closed. This is a closed set. Why? Because your space is given to be T1. And in a T1 space, every singleton set is closed. So this is a closed set, and F is also given to be closed. F is also given to be closed. Now you are having two disjoint closed sets in a normal space. And if in a normal space you have two disjoint closed sets, then definitely you will have two disjoint open sets containing them. So therefore there exist disjoint open sets G and H such that your set X is a subset of G and your set F is a subset of H. Obviously G intersection H is phi because G and H are disjoint. Now singleton set X is a subset of G. That clearly means that X belongs to G. From where have you started and at which point you have arrived? You have taken a closed set F and a point X not belonging to F, and you have obtained two open sets G and H, one containing the point X, other covering the closed set F, and their intersection is phi. That means the space is regular. T1 it is already given, so regular plus T1 it is a T3 space. So that means every T4 space is a T1 space. As I am telling you again and again that we are heading towards Urysohn's lemma, and Urysohn's lemma is the most important lemma from the point of view of examination of any syllabus of topology where separation axioms are there. So for Urysohn's lemma, one more thing is required, and that is dyadic fractions. So what are dyadic fractions is a very important thing. Dyadic fraction. What is a fraction first of all? A fraction is a rational number lying between 0 and 1. And a dyadic fraction is also a fraction, so it must also lie between 0 and 1, but it is a special type of fraction. A dyadic fraction means a fraction of the type p upon 2 raised to the power m, where p is odd natural number and is definitely less than 2 raised to the power m. Why? Because it is a fraction. So if you don't want to write less than 2 power m, it's okay because you are writing here fraction. So any fraction of the type p upon 2 raised to the power m where p is an odd number is a dyadic fraction. For example, if you take your m to be 1, so if you will take m to be 1, it is 2 raised to the power 1, that means 2. And now, since it is a fraction, your numerator must be less than denominator. So which natural number is there which is odd and is less than 2? That is 1. So 1 upon 2 is a dyadic fraction. If you take your m to be 2, here it is 2 square, that means 4. If the denominator is 4, then there will be 2 dyadic fractions. Why 2? Because there are 2 odd numbers less than 4. So 1 and 3. These are two direct fractions. For m to be 3, you will have denominator as 8. And now, look at, if your 8 is the denominator, what can be numerator to make it a direct fraction? It can be 1, it can be 3, it can be 5, it can be 7. So similarly, if you move ahead with the denominator 16, you will have 8 options for your numerator, and these options are 1, 3, 5, 7, 9, 11, 13 and 15. So these are the direct fractions and the set of all direct fractions. Set of all direct fractions p upon 2 power m, where m is a natural number and p is an odd natural number. Less than 2 power m you may write this set. That means the set of all direct fractions we usually denote it by d. So d is the set of all direct fractions. Now